Okay, we're going to do 5.44 from the end of the book. Now, or the end of the chapter. Now, this is a pretty cool problem. You're not likely to see one exactly like this on an exam, I guess. I mean, I guess you could, but it's pretty conceptual, okay? However, I chose this problem to talk about because I think that it shows some important ideas that you do need to know, okay? So in 5.44, you're given this picture at the bottom of page 249, and it's got different color spheres, and this is basically meant to be a sort of a microscopic or a molecular view of a gas. Okay, so all these different spheres are different gases, different substances. They're all existing as a gas, so they can all exert a pressure, but they're all mixed together. It's a mixture of gases, much like what you might see in a sample of air, perhaps. Okay. So there's four different substances. They call it A, B, C, and then D2. Okay, they all have their own colors. Now I don't have colored markers, so I can't show different colors. But I just tried to show different circles, and I labeled some P or G for green or purple, and these double ones are the D2s. Okay, we'll get to that here in a second. And then based upon this figure, you're asked a series of questions. Which gas has the highest partial pressure, which has the lowest partial pressure, and if the total pressure is 3/4 of an atmosphere, what is the partial pressure of this particular gas, D2? All right. So this whole problem revolves around partial pressures and the so-called Dalton's law of partial pressures. That's what they're asking you about here. Okay. First off, what is a partial pressure? Okay. Well, it's nothing more than the pressure exerted by one individual gas in a mixture. If you have a mixture like this, the cool thing about that is the total pressure, P total, is equal to the sum of the partial pressures, or the sum of the pressure of each gas. So in this case, that would be PA plus PB plus PC plus D2, they call it, where each one of these partial pressures is the pressure exerted by the number of moles of gas that's in our closed container. So the total pressure is just the sum of the partial pressures. You just add up the pressures of each component, and that's your total. Okay? So that's pretty straightforward, right? And another cool consequence of this, okay, is that the partial pressure of any one particular gas, say PA, divided by the total pressure is equal to the mole fraction of A in the mixture. And that mole fraction of A chi is the moles of A divided by the total number of moles of everything. Okay? So basically what this says is that each gas behaves independently of the others and exerts a pressure in accordance with the ideal gas law equation. So each gas in the sample behaves ideally. It follows the PV equals nRT relationship. And we just need to add up the pressures, the partial pressures of each gas, and that's our total pressure. Okay? So it's pretty straightforward. And this whole question gets at those concepts. Okay? So which one of these gases in the picture has the highest partial pressure? Well, if the partial pressure of any one particular gas scales with the mole fraction, it stands to reason that all we need to do is look at this picture, figure out how many particles of each type are present, and just pick the one which is most abundant, and that's going to have the highest partial pressure, because in the picture that indicates the highest number of moles. Okay, so what we really need to do is just make an inventory of all the substances which are present. Okay, so how many of each colored sphere? So if you look at this closely, then the purple spheres are called A, and I believe there's 1, 2, 3, 4 of those. 4 purple spheres in the picture. Now the black spheres are labeled B, and let me see how many of those we've got. I made those these singular black dots. 1, 2, 3. So we've got 3 singular black dots. And what about the greens? The greens are called C, gas C. 1, 2, 3, 4, 5. I've got 5 green spheres inside this container. And then the D2s are the molecules. Okay, so we got one here, one here, one here. And I didn't color this one in, but I should color that one in. So 1, 2, 3, 4 of the D2s. Okay, so that's our inventory, how much I've got. So which one has the highest partial pressure? Well, that's the one that's most abundant because the figure indicates that it has the highest number of moles, and the pressure exerted by any one of these gases inside of a closed container of fixed volume at a particular temperature is proportional to the number of moles, right? Directly proportional. So the highest partial pressure is the one that's most abundant. So it looks like that one's gas C. Because there's 5 of those, and that's the most abundant, right? Now likewise, the lowest partial pressure, that's the one that's going to be least abundant. In this particular case, that's going to be gas B. Lastly, the coolest one, I think, right? Number C, or letter C here. It tells us the total pressure inside that container is 0.75 atmospheres. And it wants to know what is the partial pressure of the D2. Remember earlier I said that the partial pressure of any one particular gas, reference to the total, jives with the mole fraction, right? Or the equivalent to the mole fraction. So if I count the total number of particles in my container, I just have to add up everything above. So 4 plus 3 is 7, plus 4 is 11, plus 5 is 16. So there's 16 total particles. And what fraction of that is D2? It looks like 4 out of 16, or 25%. Fractionally, that's 0.25. That's the fractional abundance of the D2, which is analogous here to our mole fraction. Okay? So what this basically tells us then is that if I take my P total and multiply it by this fractional component, I'll call that the chi-A, the mole fraction for our purposes, that gives me the partial pressure of substance A. Now here I don't want A, just to not confuse anyone, I'm going to change the A to D2, okay? Because there's something else called, I was drawing this equation in generic forms here, but we want specifically D2 here, so let's be consistent. So the partial pressure of D2 is equal to the total pressure times this fraction, okay, which we know is equal to 0.25 now. And the total pressure we were given in the problem is 0.75 atmospheres. So to find the partial pressure of D2 in this particular mixture, all I need to do is take the 0.75 and multiply it by the 1/4, or 0.25, and I get 0.1875 atmospheres, or 1/4 of the total. And this works because each of the gases in my sample behave independently from one another. They're all behaving as ideal gases in accordance with the ideal gas law. So all that's important is the amount that's there for setting the pressure at any particular temperature and volume of this container. Okay? So this is a fun little problem that's sort of rooted in the Dalton's law of partial pressures.